Welcome to today's session. In this video, we'll dive into the problem word ladder 2, a fascinating challenge that explores word transformation paths in a dictionary. We'll discuss the problem requirements, analyze different approaches, and break down the solution step by step. Let's get started. In this problem, titled Word Ladder 2, you're tasked with finding all the shortest transformation sequences between two words, begin word and end word. You're given a dictionary of valid words called word list, and each transformation must adhere to certain rules. First, every transformed word must be present in word list, and importantly, begin word itself isn't considered a transformed word. Second, only one letter can change at a time during the transformation. Additionally, each intermediate word must also be valid, meaning it must exist within word list. Lastly, you cannot have duplicate words within a sequence. If no valid transformation sequence exists, the result should be an empty list. The input consists of begin word, end word, and word list, and the output will be one or more lists representing the shortest transformation sequences from begin word to end word. To clarify the problem further, let's look at an example. Suppose the begin word is hit, the end word is cog, and the word list contains hot, dog, lot, log, cog. The output in this case will be two valid transformation sequences, hit, hot, dog, cog, hit, hot, lot, log, cog. Here's why these sequences are valid. In both cases, each step involves changing only one letter at a time, and every intermediate word exists in word list. For example, in the first sequence, hit transforms into hot, then to dot, followed by dog, and finally cog. Similarly, the second sequence achieves the same goal but follows a slightly different path through lot and log. Both sequences are of the shortest possible length, containing 5 words each. Continuing with the examples, let's consider another input. If the begin word is still hit, the end word is cog, but this time the word list is hot, dog, lot, log. Notice that cog is missing from the list. In this case, the output would be an empty list because no valid transformation is possible. Now, for a simpler case, if the begin word is a, the end word is C, and the word list contains a B, C, the output will be a C. Here, the transformation sequence is straightforward, a changes directly to C, and since C is in the word list, the transformation is valid. In the last example, the transformation sequence, C, is the shortest possible one, consisting of just 2 words, the begin word and the end word. The problem also specifies some constraints to guide your solution. For instance, the lengths of begin word and end word will always be the same, ranging from 1 to 10 characters. The word list can contain up to 5,000 unique words, all of which are lowercase English letters. It's also guaranteed that begin word and end word will never be the same. These constraints help define the boundaries within which your solution must operate, ensuring consistency and predictability in the problem setup. Finally, let's address some edge cases you may encounter. If either begin word or end word is empty, the result should be an empty list. Similarly, if the end word is not present in the word list, no transformation is possible. If the word list itself is empty, the output will also be an empty list. While the constraint ensures that begin word and end word have the same length, if this condition were violated, no transformation would be allowed. Additionally, if there are multiple shortest paths, all of them should be included in the output, and the order of these paths doesn't matter. Lastly, any words in the word list that cannot be reached from begin word are simply ignored in the transformation process. These considerations help ensure your solution is robust and handles all possible scenarios effectively. To solve the word ladder 2 problem, we considered 2 main approaches. The first is the brute force approach. The intuition behind this method is straightforward: generate all possible sequences of word transformations from the begin word to the end word, trying every valid option at each step. While this guarantees that we find all paths, it becomes computationally infeasible very quickly. For a word list of size n and word length m, the number of combinations grows exponentially, leading to a time complexity of O(m) to the power of n. This makes it impractical for even moderately sized inputs, as it doesn't take advantage of the problem structure, such as the focus on shortest paths. The second approach, optimized BFS with backtracking, is much more efficient. Here, we treat words as nodes in a graph, where 2 words are connected if they differ by just 1 character. BFS naturally explores the shortest paths first, and we use backtracking after BFS to construct all the valid paths from beginward to endward. This approach is more structured and computationally feasible while still delivering the desired results. Now, the key insight for this problem is recognizing that the shortest transformation sequence can be modeled as the shortest path in a graph. BFS is ideal for this, as it explores nodes level by level, ensuring that we process words by their shortest distance from the begin word. Backtracking complements this by allowing us to reconstruct all valid paths once BFS has established the graph structure. Here's how the process works. First, we use BFS to traverse the graph, starting from the begin word, and build a mapping of each word to its predecessors in the transformation path. We stop the BFS as soon as we reach the end word, ensuring that only the shortest paths are considered. Then, using backtracking, we trace these paths from the end word back to the begin word, collecting all valid transformations. The complexity of this approach is manageable. The time complexity is O(m*(n), where m is the word length and n is the size of the word list. Space complexity is also O(m*(n), accounting for the graph structure and visited states. While efficient, the backtracking step can still be demanding if there are many shortest paths, but this trade-off is acceptable given the guarantees on optimality and efficiency. In addition to the optimized BFS strategy, we also explored bidirectional BFS as another efficient approach. Instead of starting BFS from just the begin word, we simultaneously start searches from both the begin word and the end word. This dramatically reduces the search space, as the two searches meet in the middle. Conceptually, this cuts the depth of the search tree in half, leading to improved performance. The process involves alternating between the two searches, performing BFS one level at a time from each direction, and stopping as soon as the two searches intersect. Once this happens, we construct the graph structure to represent the connections. Afterward, like with single-direction BFS, we use backtracking to reconstruct all valid shortest paths. In terms of complexity, the time remains O(m*(n), as we still explore each word and its transformations, but the reduced depth can make the constant factor smaller, leading to faster execution in practice. The space complexity remains O(m*(n). While bidirectional BFS is often faster, it does introduce additional overhead in managing two search fronts and ensuring they interact correctly. This makes it slightly more intricate to implement. After evaluating the options, we chose the optimized BFS with backtracking approach for its balance of simplicity, efficiency, and correctness. While bidirectional BFS can provide marginal speed improvements, it introduces additional complexity that may not be worth the trade-off for typical input sizes. The chosen strategy ensures that we explore the shortest paths first through BFS, and the backtracking step guarantees that all valid transformation sequences are captured. This method is intuitive and aligns well with the problem's requirements, offering acceptable performance within the given constraints. By leveraging the structure of the graph and focusing on the shortest paths, we achieve an approach that is both practical and effective. In this problem, we are tasked with finding the shortest transformation sequence from a given word, called begin word, to a target word, called end word. To achieve this, we can only change one letter at a time, and each intermediate word must exist in a given dictionary of valid words. This problem can be visualized as finding the shortest path in an unweighted graph, where each node represents a word, and edges connect words that differ by only one letter. To solve this efficiently, we will use the breadth-first search, or BFS, algorithm. The first step in our approach involves pre-processing the word list to generate intermediate patterns. For each word, we calculate all possible intermediate forms by replacing one character at a time with a wildcard symbol, like an asterisk. These patterns are then stored in a dictionary, where the keys are the patterns and the values are lists of words that match those patterns. For example, if the word list includes hot, dot, and lot, the intermediate pattern *ot would map to all three of these words. This pre-processing step enables us to quickly find all valid transformations for any given word, significantly improving the efficiency of the BFS algorithm. Once we have pre-processed the word list, the next step is to initialize the BFS. We start by setting up a queue, where each entry is a tuple containing a word and the current transformation depth. The queue is initialized with the begin word at a depth of 1, indicating the starting point of our transformation sequence. Additionally, we maintain a visited set to track words that have already been processed. This prevents cycles in the graph and eliminates redundant work, ensuring that each word is visited only once. With these preparations in place, we proceed to perform BFS. While the queue is not empty, we repeatedly dequeue the front element, which gives us the current word and its associated depth. For each intermediate pattern of the current word, we look up its neighbors in the pre-processed dictionary. If a neighbor matches the end word, we can immediately return the depth increment by 1, as we have found the shortest transformation sequence. Otherwise, if the neighbor has not been visited, we mark it as visited and enqueue it with an increment depth. This process ensures that we explore all transformations at the current depth before moving deeper, a key property of BFS that guarantees the shortest path. To better understand how BFS works in this context, let's go through an example. Suppose the begin word is hit, and the word list includes hot, dog, lot, log, and cog. Starting with hit, we generate its intermediate forms, *it, h*t, and high*. Among these, the pattern h*t has a match in the dictionary, namely, the word hot. We then enqueue hot with a depth of 2, marking it as the next word to process. As we continue, we dequeue hot and repeat the process for its intermediate forms. This systematic exploration ensures that we gradually build the transformation sequence until we either find the end word or exhaust all possibilities. Additionally, it is important to handle edge cases. If the end word is not in the word list, we can immediately return 0, as no valid transformation exists. Similarly, if the BFS queue is emptied without finding the end word, we also return 0, indicating that there is no path between the given words. The BFS approach relies on several key insights and data structures that ensure its efficiency and correctness. First, BFS is particularly well suited for this problem because it guarantees the shortest path in an unweighted graph by exploring all nodes at the current depth before moving deeper. The use of intermediate patterns, such as *OT or h*t, is another crucial optimization. These patterns allow us to efficiently find all valid one-step transformations without explicitly generating all possible combinations. Additionally, the visited set plays a critical role in preventing cycles and redundant processing, ensuring that each word is visited only once. From a data structure perspective, we use a dictionary to map intermediate patterns to words, enabling O1 access to neighbors. The BFS itself is implemented using a queue, which stores the current word and its transformation depth. Finally, the visited set tracks words that have already been processed, further optimizing the algorithm by avoiding repeated work. Let's apply this approach to a concrete example. Given the begin word hit, the end word cog, and the word list, hot, dog, lot, log, cog, we first pre-process the word list to create the intermediate dictionary. This dictionary maps patterns like *OT, h*t, and ho* to their corresponding words. For instance, *OT maps to hot, lot, while h*t maps to hot. Once the pre-processing is complete, we initialize the BFS. The queue starts with the tuple hit 1, indicating that we begin with the word hit at a depth of 1. The visited set is also initialized to include only the begin word, ensuring that we don't revisit it during the search. With these preparations, we are ready to begin the BFS process to find the shortest transformation sequence. During the BFS, we dequeue the first element in the queue, which is hit 1. We then generate the intermediate forms of hit, such as *it, h*t, and high*. Looking up these patterns in the intermediate dictionary, we find that hot is a valid neighbor through the pattern h*t. We then enqueue hot with a depth of 2 and add it to the visited set. The BFS continues by dequeuing hot and processing its intermediate forms in a similar manner, eventually reaching the end word cog. Once cog is found, we return the transformation depth, which in this case is 5. This corresponds to the shortest transformation sequence, hit-hot-dot-dog-cog. By leveraging BFS, intermediate patterns, and the visited set, we efficiently solve the problem and guarantee the shortest path. This implementation solves LeetCode problem number 126, word ladder 2, which involves finding all shortest transformation sequences from a start word to an end word using a given dictionary of valid words. The solution uses a BFS-based approach for efficiency. First, we convert the word list to a set for faster lookups. If the end word is not in the set, we can return an empty list immediately since no transformation is possible. We initialize layer as a dictionary where keys are words and values or lists of paths leading to those words. It starts with the begin word as the key and a path containing only itself. A while loop processes layer level by level. For each word in the current layer, we check if it matches the end word. If so, we return the associated paths since we have found the shortest transformation sequences. For each word, we generate all possible one-letter transformations by iterating through its characters and replacing each with every letter from A to Z. If the new word exists in word list, we add it to the new underscore layer along with the extended paths that lead to it. After processing a layer, we remove the words in new underscore layer from word list to prevent revisiting them, and update layer for the next BFS iteration. If the loop completes without finding the end word, we return an empty list as no transformation sequence exists. This approach ensures that we explore all shortest paths in a level order fashion, making it both time efficient and memory efficient for this problem. Here, we start with the Java implementation for solving word ladder 2. First, we import the necessary libraries, including Java's utility collections. The method findLadders takes 3 parameters: the starting word, the target word, and the word list. We begin by converting the word list into a hash set for fast lookups. If the end word is not in the set, we can directly return an empty list since no transformation is possible. Next, we initialize a hash map called layers to keep track of all paths leading to each word during the transformation process. Initially, we add the begin word with its own path as the first entry in the map. Then, we enter a while loop to process the layers. As long as there are words to explore, we create a new hash map, new layers, to store the next layer of transformations. For each word in the current layer, we check if it matches the end word. If it does, we return all the paths leading to it, effectively solving the problem. If not, we attempt to transform the word one character at a time by iterating through its length and substituting each character with letters from A to Z. When a valid transformation is found, meaning the new word exists in the word set, we prepare to add it to the next layer. If the new word does not already exist in new layers, we initialize it with an empty list to store its paths. Then, for every path leading to the current word, we create a new path by copying the existing one and appending the new word. This ensures that each transformation step is properly tracked, and the paths are updated in new layers. Once all transformations for the current word are processed, we continue iterating through the rest of the words in the current layer. After processing all words in a layer, we remove the newly transformed words from the word set to prevent revisiting them, and we update layers to point to new layers, effectively advancing to the next level of transformations. If the end word is never reached during this process, we exit the loop and return an empty list as no valid transformation sequence exists. This implementation ensures that we explore all shortest transformation sequences efficiently using a breadth-first search approach while maintaining the paths through the layers map. To solve this problem, we start with the given input: the begin word is hit, the end word is cog, and the word list contains hot, dog, lot, log, cog. First, we convert the word list into a set for faster lookups, which gives us hot, dog, lot, log, cog. Since the end word, cog, is present in the word list, we proceed with the solution. We initialize a dictionary called layer, where each key represents a word at the current breadth-first search (BFS) layer, and its value is a list of all paths that lead to that word. Initially, layer contains only the begin word, represented as hit. Now, we start the BFS process. For the first layer, we process the word hit. We generate all possible one-character transformations of hit by changing one letter at a time. Among these transformations, hot is a valid word in the word list. We add hot to the new underscore layer with the updated path, hit, hot, and remove it from the word list. After processing, the layer is updated to hot, hit, hot, and we move on to the next layer. At this point, we process the layer containing hot, hit, hot. For the word hot, we generate all its valid one-character transformations. The words dot and lot are valid transformations found in the word list. For each of these words, we create new paths leading to them and add them to the new underscore layer. The paths added are hit, lot, hit, hot, lot. After processing hot, we remove dot and lot from the word list, leaving dog, log, cog. The layer is then updated to dot, hit, hot, dot, lot, hit, hot, lot. In the next layer, we process dot and lot. For dot, the valid transformation is dog, and for lot, the valid transformation is log. We update the paths in new underscore layer to include dog, hit, hot, dot, dog, log, hit, hot, lot, log. After processing these words, we remove dog and log from the word list, leaving only cog. The layer is updated to dog, hit, hot, dot, dog, log, hit, hot, lot, log. Finally, we process the next layer containing dog and log. Both words transform into the end word, cog. We add the paths leading to cog as cog, hit, hot, dot, dog, cog, hit, hot, lot, log, cog. Since cog matches the end word, we return all the paths. The output for this example is the set of valid word ladders that transform the begin word, hit, into the end word, cog, using the shortest sequence of transformations. The result is hit, hot, dot, dog, cog, hit, hot, lot, log, cog. These two paths represent the shortest transformations, and they include only valid words from the given word list. Now, let's analyze another scenario where no valid transformations are possible. In this case, the input has begin word as hit, end word as cog, and word list as hot, dot, dog. After converting the word list into a set, we get hot, dot, dog. Here, we immediately notice that the end word, cog, is not present in the word list. Since it's impossible to reach cog, we return an empty list as the output. In this next example, we consider a simpler case where only one possible path exists. The begin word is a, the end word is C, and the word list contains a, B, C. After converting the word list to a set, we have a, B, C. Since the end word, C, is present in the word list, we can proceed with the solution. We initialize layer as where the starting word is the initial key, and its value is a list containing the path, a. For the first BFS layer, we process a. The only valid transformation is B, which is in the word list. We add B to the new underscore layer with the path, a, B, and remove it from the word list, leaving C. The layer is then updated to B, a, B, and we continue to the next layer. In this layer, we process B, which is the only word in the current layer. The valid transformation for B is C, and since C is in the word list, we add it to the new underscore layer with the path, a, B, C. As C matches the end word, we stop the BFS process and return the path, a, B, C, as the output. This single path represents the shortest transformation from A to C, and it includes only valid words from the word list. This concludes the example where there is a single valid transformation path. Here, we analyze the time complexity of the solution. First, let's consider the process of word transformations. For a word of length L, we can generate 26 possible transformations for each of the L positions, resulting in a transformation cost of O, L*26, per word. Next, we have the breadth first search traversal. In the worst case, BFS will process all N words in the word list. Combining the transformation cost with BFS traversal, this step contributes O, and *L*26. Additionally, there is the path construction step, where we store all possible paths leading to each word. If there are P paths to a word, the cost of constructing new paths for its transformations is O, P*L. In the worst case, every word could have up to P_max paths, adding a complexity of O, P_max *N*L. When we combine these factors, the overall time complexity is approximately O, N*L*, 26 plus P_max, which simplifies to O, N*L*, P_max, in cases with significant path branching. Now let's delve into the space complexity. The first component is the storage of the word list, which is stored as a set and takes up O, N, space. Then, we have the layer dictionary, which stores all paths to each word. Since each path has a length of up to L and there can be as many as P_max paths per word, storing paths for all N words requires O, P_max *N*L, space. Similarly, the new underscore layer dictionary, which temporarily holds the paths for the next BFS level, also contributes p underscore max asterisk n asterisk l space during traversal. Finally, auxiliary variables such as new underscore word occupy negligible space in comparison. When we combine these components, the overall space complexity is dominated by the storage of paths, leading to p underscore max asterisk n asterisk l. Looking at the best, average, and worst cases, in the best case scenario, the BFS identifies the shortest path early without needing to store many paths. Here, the complexity is dominated by BFS traversal, approximately n asterisk l. In the average case, BFS explores multiple paths to the n-word, with moderate branching, leading to a complexity of n asterisk l asterisk p underscore max. Meanwhile, the worst case occurs when all words in the list are part of multiple paths, and BFS must explore all combinations, resulting in both time and space complexity of n asterisk l asterisk p underscore max. A comparison with a brute force approach highlights the efficiency of BFS. A naive method would involve generating all possible transformation sequences and checking their validity, leading to factorial complexity n, which is highly inefficient. In contrast, BFS systematically explores only valid transformations and prunes irrelevant paths, achieving a much more efficient complexity of n asterisk l asterisk p underscore max. Finally, the mathematical proof underscores why this complexity is consistent with the algorithm structure. BFS constructs paths level by level, ensuring no redundant paths are explored. The cost of transforming a word is l asterisk 26, and with at most n words to process, this accounts for the traversal cost. The number of paths stored is determined by the branching factor, represented as p underscore max. These factors, together, validate the derived complexities of n asterisk l asterisk p underscore max, for both time and space. This systematic breakdown demonstrates that the BFS-based solution is both mathematically sound and computationally efficient for solving the word ladder 2 problem. When solving the word ladder 2 problem, several common mistakes can significantly impact performance and correctness. First, not using a dictionary or set for word lookup is a frequent issue. Without it, the algorithm ends up performing n asterisk m checks, where n is the size of the word list and m is the word length. This can be dramatically improved to 1 by leveraging a hash-based lookup. Another mistake is ignoring bidirectional search. Many implementations use unidirectional BFS, but bidirectional BFS is far more efficient as it reduces the search space, especially for larger word lists. Then, there's the issue of not validating input properly. For example, if the n word is missing from the word list or the word lengths don't match, it can lead to runtime errors or incorrect results. Revisiting words during BFS is another pitfall. If you don't mark words as visited, the algorithm may revisit the same transformations repeatedly, causing infinite loops or unnecessary work. Lastly, inefficient string transformations can slow things down. Instead of generating every possible transformation naively, a smarter approach involves pre-computing patterns, which eliminates repetitive checks and speeds up the process. To excel in interviews, there are a few critical insights to keep in mind. First, optimization is a key focus. Start by explaining a brute force approach to show your understanding, but quickly pivot to optimized solutions like BFS or bidirectional BFS. This demonstrates efficiency. Next, be ready to handle edge cases. Interviewers often test scenarios such as no valid transformation paths, empty word lists, or transformations requiring revisiting the same word multiple times. Handling these gracefully is essential. Additionally, recognize the underlying pattern of this problem. It's fundamentally a graph traversal problem. Drawing parallels to shortest path problems highlights your broader conceptual understanding and helps you explain your approach more effectively. Finally, it's helpful to connect this problem to related ones. For instance, LeetCode 127 focuses on finding the shortest transformation sequence, while this problem extends to finding all valid shortest paths. Other problems like open the lock and minimum genetic mutation also involve BFS-based shortest path solutions, offering you a chance to showcase your versatility. For alternative approaches, consider bidirectional BFS as an excellent optimization. It reduces the search space by exploring from both the begin word and end word directions simultaneously. However, it does come with added complexity, as you need to synchronize the two queues. Another option, though less common, is ** search. This uses a heuristic, such as the number of differing characters between words, to guide the search. While it can seem promising, it introduces the overhead of maintaining a priority queue and isn't always more efficient than BFS for this specific problem. Lastly, there's graph preprocessing. This involves pre-computing valid transformations using wildcard patterns, such as replacing a character with **. For example, the word hot could generate patterns like H**T. Although the preprocessing step has a higher upfront cost, it significantly accelerates BFS traversal by narrowing down the possible transformations quickly. Thank you for following along. We covered the key ideas and techniques to solve word ladder 2 efficiently, focusing on BFS and backtracking. Remember to practice graph-related problems to strengthen your understanding. Don't forget to like, subscribe, and share this video for more tutorials. See you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!